All right, welcome. In this video, we're going to discuss some more things about solutions. In a previous video, we discussed what solutions are, and we started to discuss a little bit why certain things will dissolve and why they won't, and we're going to get into that into more detail here. So something to keep in mind with solutions is that when you mix two things together, there's a natural tendency of those two things to just get mixed up, and that has to do with entropy, which we'll talk about later on in the year. But the key thing to know for right now is that mixing is going to occur spontaneously unless there is something that is restraining the substances. And the restraint might be a physical barrier, like in this example down here. We can see we have like salt water separated from pure water, and when we remove this barrier, they will just get mixed up and make a uniform concentration. Or it could be that that thing holding them apart could be an intermolecular force or a bond. So it could be an attraction that's kind of holding them apart. So when we're thinking about predicting whether solutions will form or not, we want to consider these three different types of attractions. So you want to consider the attractions of the solute to itself, right? So like let's look at sugar in water. Sugar dissolved in water, whereas sugar is the solute and water would be the solvent. So what we have to consider is we have to consider the strength of attraction between those sugar molecules. So how strongly are sugar molecules attracted to themselves? We have to consider the attraction between water molecules. So how strongly does the solvent attract to itself? And then we want to consider the strength of the attraction between the solute and the solvent. And whether or not a solution will form is going to be based upon like the magnitude of all these different attractions here. So if something dissolves, that means the attraction between the solute and the solvent is sufficiently strong to kind of overcome these attractions. If something does not dissolve, that means that one or more of these initial attractions is like too strong. So like if sugar is too attracted to itself, then it won't want to stick with the water. It'd rather just stick to itself. So let's look at an example of something that is not soluble and kind of think about why it does not dissolve. So an example would be hexane and water. This is really similar to what you probably haven't dealt with hexane in your house because that's not super safe to have around your house, but you've probably seen oil and water, which is a very similar thing happening. So when you mix oil and water together, they don't mix. So let's take a look at why that is. So we want to think about the various attractive forces here, right? So between the solvent-solvent attraction, between the water molecules, that is hydrogen bonding. So water molecules attract to themselves by hydrogen bonds. So that's a pretty strong attraction. Your hexane is nonpolar, so we'll call hexane your solute in this case. And then since it's nonpolar, it only experiences dispersion forces with itself. So those are weaker. And then let's consider what the solvent-solute attraction is. And since this is nonpolar and this is polar, they can't hydrogen bond, they can't dipole-dipole, right? Because they're not both polar. So the only attraction they're going to feel is dispersion forces. So the attraction of the solvent to the solute is relatively weak compared to this like attraction of water to itself. So what happens is the attraction between hexane and water is relatively weak. They're only attracted by dispersion forces. It's not strong enough to overcome the attraction of water molecules to each other. So the reason why they don't mix is because the attractive forces between the water molecules is what's preventing them from mixing. So basically water would rather stick to other water molecules than it would to hexane, because the attraction of the solvent to itself is very strong. So it'd rather stick to itself than mix with your hexane here. We notice that with ionic compounds, some ionic compounds dissolve and some don't. So let's take a look at what the interactions are here. So the solute interactions, well, in this case here, let's say the ionic compound would be the solute, And we're looking at aqueous solutions here, so water would be our solvent. Okay, so in order for a ionic compound to dissolve, you're going to have to overcome the attractions of the solute to itself. So you're going to have to overcome that, ionic bond there between the cations and the anions there. Then you also have to overcome the attraction of the solvent to itself. So your water molecules are attracted to themselves by hydrogen bonding. And then the new attraction that would form between the water and the ion, so like the solvent-solute attraction, would be an ion-dipole attraction. And this is true no matter what ionic compound we're talking about. And so what we see with ionic compounds, though, sometimes they'll dissolve and sometimes they won't. So sometimes this ion-dipole force is like strong enough to overcome, it's like sufficiently strong to kind of overcome this hydrogen bonding and this, attraction between ions there, and will allow them to mix. And sometimes it's not. So like over here with silver chloride, since silver chloride does not dissolve, that tells us that solute attractions are not strong enough to overcome the other attractions. Over here, silver nitrate, it does dissolve. So in this case, the solvent-solute attractions are strong enough. And here's kind of a table that kind of goes over the different scenarios, whether the solvent-solute attractions are stronger or equal to or not as strong than the original interactions here. And with ionic compounds, there's not a good way of like predicting, why does silver nitrate soluble and silver chloride is not. We're not going to be able to predict that. So we will find in a later unit that we'll talk about the solubility rules, where we're just going to kind of memorize some rules. These compounds tend to be soluble, these don't. It's kind of hard to predict which ones will dissolve or not. So this is one of those rare things that we're just going to memorize, solubility rules. Okay, let's look at an example of something that does dissolve. So if you have polar mixed with polar, so like in this case, we're mixing together ethanol and water. And this is what ethanol looks like. And notice how there's an O bonded to an H, so it's capable of hydrogen bonding. And then we're familiar with what water looks like. So if you look at again, we're comparing these three, attractive forces. So the solute, this is your ethanol. It can hydrogen bond to itself. Your solvent can hydrogen bond to itself. And then they can also hydrogen bond to each other. So the solvent-solute attraction is hydrogen bonding. So all three intermolecular forces are comparable. So there's nothing preventing them from mixing. So they're about as attracted to each other as they are to themselves. So they're going to want to mix together. And so it will dissolve. Okay. And here's a visual showing, like if you look at the example of sugar and water, sugar will dissolve in water. And if you, let's look at these kind of three categories of forces again. So if the solute is sugar, it can H bond with itself. You see how these red ones are oxygens and these white ones are hydrogens. So we see that sugar has a bunch of OHs, so it can hydrogen bond with itself. The solvent is water, so it can also hydrogen bond with itself. And then when you mix together the solvent and the solute, we see that these solvent-solute interactions are also, are also hydrogen bonds. So that is why sugar will dissolve in water fairly well, is because it's got a relatively strong attraction to water. It is at least as strong, if not stronger than these attractions, so that's going to allow them to mix together. So thinking about hydrogen bonding in mixtures, this is a key kind of visual to look back at, like kind of a definition of what is a hydrogen bond. So a hydrogen bond is when you have an H covalently bonded to an O, N, or F. This hydrogen is when it's attracted to an O, N, or F in a nearby molecule, this is a hydrogen bond. So this hydrogen right here is capable of hydrogen bonding with a nearby molecule. This hydrogen over here is not capable of hydrogen bonding because this hydrogen is covalently bonded to a carbon. So in order to hydrogen bond, your hydrogen has to be covalently bonded to an O, N, or F. This is a really key thing to keep in mind. You might be asked to draw a hydrogen bond or identify whether certain things are hydrogen bonds or not. So this visual can be helpful to look back at. All right, other thing we want to think about with solutions is we'll notice that when you dissolve things in water, sometimes you create a solution that will conduct electricity, and sometimes you don't. And in this example right here, we see that if we have a ionic compound on its own in the solid form, it does not conduct, but when you dissolve it in water, it does conduct. And the reason why is because conducting electricity requires free moving charged particles. So you need two things. You need to have charged particles, they need to be able to move around freely. So in a solid, you've got the charged particles, but they're locked in place. They can't move around. So these are not going to conduct. But over here, when you dissolve ionic compounds in water, what happens is they separate. They dissociate is a word we sometimes use. And they split apart into ions. So we might say ionized. Well, I don't know if that's I'd say more dissociate. I think is appropriate here. And that compound splits apart into ions that are now moving around freely because they're in liquid water. And so this can conduct electricity. So this slide goes over what we just talked about here. So electricity is conducted through the movement of charged particles. And in a solution, when you have dissolved ions, they can move around freely. That's what allows your ionic solutions to conduct well. In metals, FYI, the reason why metals conduct electricity well is because of that sea of electrons model there. Those electrons are not locked in any one particular place. They can move around freely throughout the whole sample, and that's what allows you to conduct electricity. And so when you when something dissolves in water and then it conducts electricity, we call that substance an electrolyte. So that's the word for it. You may have heard people talk about that, like with Gatorade. We've got electrolytes. Basically means we have some salts dissolved in water. That's what that means. And so ionic compounds, when you dissolve them in water, they're what we call strong electrolytes. So they'll totally dissociate into ions, and that will allow them to conduct electricity. Molecular covalent substances typically are non-electrolytes. They will not dissociate into ions. There is an exception. Acids are an example of a molecule which is molecular covalent. So like this right here, you can see it's all nonmetals, so it's molecular covalent. But when you stick it in water, it actually will ionize a little bit. So it'll form some ions, and so it will actually be an electrolyte. So in general, ionic things are electrolytes because they form ions. Molecular covalents tend to be non-electrolytes. But there's an exception here with our acids. Acids are molecular covalent, but they are actually electrolytes. So we will talk more about acids in like unit 7. So we will come back to that later. Here's our, going back to the idea of what's going on in metals, here's our visual showing what's going on with metals and why they can conduct electricity. And here's our visual showing what's going on with our acids. All right. And so that's it for this video. We'll go over practice problems in a different video. Thanks for watching.